Good afternoon. Once again, I'm honored to welcome you to our virtual lecture series. We created this series to showcase the work of some of our world-renowned researchers here at Carnegie Institution for Science, which for more than a century has delved into the deepest secrets of the universe, from the genetic mechanisms of evolution all the way to the furthest reaches of the cosmos. And we greatly appreciate this opportunity to share our research with you. I'm honored to co-host today with Robert Shelton, president of the Giant Magellan Telescope organization. And today we will hear from astronomer Rebecca Bernstein. Dr. Bernstein has been a Carnegie scientist who now serves as the project scientist for the GMT, or the Giant Magellan Telescope. And in that role, she's been providing technical and scientific leadership for the telescope's design and construction. In her work with the GMT, Dr. Bernstein is extending Carnegie's century-long reputation for building some of the most powerful telescopes in the world, from the telescopes on Mount Wilson, just above Pasadena, which, by the way, was built at a time when they needed mules and carts to haul delicate equipment up the hillside, to Mount Palomar Observatory, which made it possible for astronomers to look more deeply into space and study the structure of the universe and the evolution of stars, and now to Las Campanas Observatory in Chile, where we use a suite of exceptional telescopes to make groundbreaking discoveries. We began building Las Campanas Observatory in the Atacama Desert 50 years ago, because in the high desert, the air is clear, it's dry, and it's really perfect for astronomy. And now we're really excited, very proud, in fact, that the GMT, the Giant Magellan Telescope, is being built at Las Campanas. The GMT, as you'll hear from Rebecca, is part of a whole new generation of ground-based, extremely large telescopes. And when this telescope is commissioned, about 9 years from now, it will provide revolutionary levels of resolution and sensitivity. Dr. Bernstein brings a wealth of talent and experience to her work on the GMT. She's a gifted instrumentalist who has designed and built important pieces of equipment. After she finished her PhD in astrophysics at Caltech, she came to Carnegie on a NASA Hubble postdoctoral fellowship. And while she was here, she led the development of a high-resolution spectrograph for one of our other telescopes, the 6.5-meter Magellan Telescope, which is down at Las Campanas. And later, as a professor at the University of Chicago, she was a member of the core design team that developed the original concept for the GMT. But even more importantly, Dr. Bernstein is a leader in shaping the scientific mission for this incredible new telescope. You see, we don't build these huge telescopes, better telescopes, because of some kind of astronomical arms race. We actually build them because, of course, they provide incredible discoveries. And this particular telescope is very exciting. Using the GMT, we'll look more deeply into the secrets of the universe. We'll gain new insights into the nature of dark matter and dark energy, into the history and formation of the galaxies, and explore the possibility of life on planets beyond our own solar system. So like you, I'm very much looking forward to hearing Dr. Bernstein talk about the GMT and the science it will make possible. So please join me in welcoming Dr. Bernstein.
Hi, sorry about that. It took me a second to unmute. Let me share my screen so that you can see my first slide. Okay, there we go. So I think you can see that now. It's really a pleasure to be talking to you today about GMT. And thank you, Eric, for that generous introduction. And it is especially a pleasure to be talking about GMT in the Carnegie Lecture Series, because Carnegie has been my home for so long throughout my career. And in these strange times, it's really wonderful that we can still find a way to get together like this. So I wanted to here in the common desert, because talk in the middle of the pandemic, it really thinking about why we choose to do astronomy, or why I've chosen to do astronomy and build instruments and telescopes, and why we're all working so hard at GMT to build this giant telescope now. And by extension, why all of you should care about astronomy. So this first picture, I think, is the first step in answering that question, because I doubt that any one of us can look at this image and not feel some awe and curiosity about our place in the universe. These are pictures that were actually taken at the dedication of the Magellan Telescopes in December 2000. So that's me on the left with Bruce Bigelow, and it's actually me again on the right with a couple of people who may be joining us today, Bob and Bethany Millard. And we're looking through an eyepiece that was put on the telescope that night so that we could each look directly through the telescope. And it was quite an amazing experience. But I was at that dedication because I was working, as Eric just mentioned, with one of my Carnegie colleagues and mentors, Steve Scheckman, to build one of the first spectrographs for Magellan. And it was honestly about the most fun I've ever had in my career, actually. And Bruce there was building one of the other first generation spectrographs. So as you can see from these dates, I, like many of my colleagues at Carnegie and GMT, have spent essentially my whole adult life building spectrographs and telescopes and using them to study the universe. And I haven't just done that because it's fun, which it absolutely is, but because I think it's important and we think it's important. And we are definitely not the first people to feel this way. So these are cave drawings that were found in France. And they're not just pictures of animals. These are the first known records, drawings really, of the constellations. These are star maps. So this is the first record we have of naked eye astronomy. Now we can guess that these drawings may have been used to represent dates or events or keep track of the passing of the seasons. But one thing they clearly show is an awareness and interest in the night sky and maybe an effort to understand the world around them. So to me, this curiosity about the universe around us and this drive to understand our world and to understand our place in it, this is the thing that makes us human. And maybe it's the most important thing. And even in the middle of a global pandemic, it's important. So in this talk, I want to share with you what we're building with the GMT and why I think it's important. Okay, so because I only have about 20 minutes, I am going to jump fast forward about 16,000 years, all the way to Galileo. We're going to skip all the way over naked eye astronomy to the first use of a telescope to look at the sky. And this was an amazing milestone because our ability to see the universe is limited by the sensitivity of our eyes. And by using telescopes, we can literally focus light, more light into our eyes to let us see fainter objects. So with this first telescope, Galileo made many amazing observations of the night sky, but the one I want to focus on is the observations of the moons of Jupiter. So by watching the motion of 4 stars and by carefully recording their positions for just a few nights, he was able to infer that those stars weren't just near Jupiter in the sky, but they were actually orbiting Jupiter. And seeing that made him realize that the Earth was not at the center of everything that we see in the sky. And by extension, that the Earth is not the center of the universe. And this was a major shift in mankind's perspective. It was also a crucial clue to the mystery of planetary motion, which was solved by Kepler, and it laid the groundwork for Newton to develop his theory of gravity, namely that there's a gravitational force between all objects, that is between all masses, that holds the planets in particular in orbit around the sun. So that, I'm bringing this up because that was one of many, and maybe one of the first most important, really revolutionary discoveries about fundamental physics that shows that the universe is really the ultimate physics lab. And now I want to jump to the discovery of one of the most important tools for astronomy, which is spectroscopy. So this illustration shows Newton taking the first spectrum of sunlight in his lab and realizing for the first time that what looks like white light to our eyes is actually a mixture of light with different amounts of energy. So what's happening here is that the path of the sunlight is being bent by different amounts as it goes through the prism, depending on the energy level of the light. And we see those different energies as different colors, hence the rainbow of sunlight on his wall that we see. And it took about 50 years before Fraunhofer was able to make a sharp enough, broadly enough dispersed spectrum that he was able to see that some of the colors in that spectrum were missing. And we know now that those missing that missing light, those missing photons, are caused by chemical elements that only interact, which is absorb or emit, photons of specific energies or wavelengths. So what's happening here is that chemical elements in the atmosphere of the sun have absorbed light at specific energies that we see missing here. So that's telling us the chemical composition of the sun. Okay, so this is huge. This is huge. This means that the light coming to us from any objects anywhere in the universe will reveal the chemical composition of those objects. And I don't have time to explain how, but another important thing to understand is that spectra can also be used to figure out the motion of objects using Doppler shifting of light. So this represents really the birth of spectroscopy. It's the start of our ability to study the objects that we can't travel to. And from here, astronomy really took off. So we're going to fast forward again another 100 years to the 100-inch Hooker telescope at Carnegie's Mount Wilson Observatory. And at the time that this was commissioned, it was the largest telescope ever built. And it gave observers more than 100,000 times more light collecting power than the naked eye. So in the intervening 100 years, astronomy had again and again a huge impact on our understanding of the universe and fundamental physics. But I'm going to skip straight to one of the most important discoveries, which was actually made by Carnegie astronomer Edwin Hubble at Mount Wilson. And what you can see here on the right-hand side is a photographic image, which was the state-of-the-art astronomy data at the time. And what you see in that image is point-like stars and a few extended objects. And at that time, they didn't know if the extended objects were clusters of stars in our own galaxy or whether they were galaxies beyond our own. But Hubble was able to prove for the first time that those objects, which were called nebulae at the time, were in fact other galaxies. And he did that by measuring the distance to those galaxies using rare stars called Cepheid variables. But he did something else extraordinary, which is that he measured how fast those galaxies were moving using spectroscopy. And by plotting the distance to those galaxies against their velocity relative to us, he learned that the universe is expanding. Okay, so let's take stock for a minute. In only about 100 years of astronomy and using telescopes, mankind went from thinking that we're the center of the universe to realizing that we are anything but the center of the universe. And in fact, the universe is actually evolving. We discovered gravity. We learned how stars form and produce energy. We verified Einstein's theory of general relativity, and the list goes on and on and on and on. And all of that is driven just by looking at the night sky. Okay, so let's fast forward again. I want to focus now on what we've been able to learn in the last 25 years with the current generation of telescopes. And as we talk about that, I want to highlight what questions we still can't answer with those telescopes. Okay, so let's start nearby. By about 1995, astronomers had in fact discovered the first planet around another star. And in fact, it was a solar type star, no less. And in the 25 years since that, we've discovered over 4,000 planets around nearby stars. And even more amazing than that is that of those planets, hundreds are at the right distance from their parent star to have liquid water. So that just right distance is what we call the habitable zone of the parent star. And based on the fraction of nearby stars that have planets in the habitable zone, we can estimate that there are about 40 billion habitable zone planets in the Milky Way. And some fraction of those are the right size and density to be like the Earth. So this immediately begs a lot of questions that we would want to answer next. So some of the obvious questions are, how do those planetary systems all form? Is there another Earth out there, or maybe even many Earths? And do any of those planets support life? And I know that it's the last question that got your attention, so let's talk about that one. So to answer that question, we are not going to look for signals of little green men, although that would be very exciting or alternately terrifying, depending what kind of movies you've been watching in lockdown. But no, we're not going to look for little green men. What we're going to do is study the atmospheres of those planets using spectroscopy. And we're going to use those spectra to try to find the signature combination of molecules that can only be generated and sustained in a planet's atmosphere by life as we understand it. So we've already started studying the atmospheres of exoplanets in this way, but most exoplanets are too distant for us to take spectra of them with the current generation of telescopes. So in order to study enough planets, we're going to need bigger telescopes. So that's one of the things we've learned nearby. Let's go to the other side of the universe and talk about galaxy formation. So this is a close-up of an image taken with the Hubble Space Telescope. It's called the Hubble Ultra Deep Field, and it's in fact the most expensive image that's ever been taken. But this image is special because in it you can see objects that are about 100 million times fainter than you can see with the naked eye. And some of the galaxies in this image are faint because they're just intrinsically faint. They don't contain many stars. But some of them are faint because they're distant. And let me point out a few of them. So these distant objects, and the fact that we can see these distant objects, that's what we mean when we say this is a deep image. So by taking spectra of these faintest objects, we know that the ones I've circled are some of the more distant ones in here, and that they are in fact over 13 billion light years away. So what that means is that the light that is traveling to us from those objects has taken more than 13 billion years to get here. So basically what we're looking at here in these little postage stamp close-ups is baby pictures of the first galaxies. So what's next? Well, we don't just want to count these objects, we want to actually understand them. We want to know their chemical composition, how they formed, how they evolved into the galaxies we see around us and nearby. But frustratingly, we can't study these objects in very much detail yet. It's clear already from the spectra that we've taken that they formed only about 300 million years after the Big Bang, which is astoundingly fast. But to learn more than that, we're going to need to be able to collect more light and make sharper images. Again, that means we're going to need bigger telescopes. So before we get to talking about GMT, I want to mention just two more discoveries that really point out a gap in our current understanding of fundamental physics. So the first one I want to mention is that most of the mass in galaxies is not normal mass. And we know this by comparing the motion of stars in those galaxies, which tells us the total mass, to the total light we see from those galaxies. And what I mean by normal mass is baryonic mass, which is protons, neutrons, electrons, basically everything that makes up you and me and stars and gas, and basically all the matter in the universe that absorbs and emits light. So if most of what makes up galaxies is not normal matter, meaning it does not interact with light, then what is it? Well, we don't know. We call it, but that's just the name we've given to sort of summarize our ignorance about it. We don't know what kind of particles make up dark matter. And that's a gigantic hole in our understanding of the universe and fundamental physics. So here's my next example. Let's come back to Edwin Hubble's discovery of the expansion of the universe. So remember, one of the basic tenets of scientific discovery is that results should be repeatable and verifiable. And so, of course, a lot of work has gone on in the last 100 years to try to confirm his amazing discovery. And it has been confirmed. In fact, it's been more than confirmed. The plot on the right shows that using modern data from different methods and scientific groups and telescopes, we've confirmed not only that the universe is expanding, but that the rate of that expansion is accelerating with time, which is exactly the opposite of what the physics we understand tells us should be happening. So again, we use the term dark energy to explain the physics that we don't understand, the physics that might cause this acceleration. But there are currently no theories that can explain this observational fact about the universe. And that is again, big problem for fundamental physics. So we're missing something big, and we're not going to figure it out by sitting around twiddling our thumbs, is what I was going to say. But we're not going to figure it out without gathering more information about the universe around us. Okay, so I've explained some of the questions we have, but now I want to give you a more visceral sense of what it really means to collect more light and get sharper images, and how that gives you more information. So I have a few examples here. All right, so what I'm showing you is an image of something. You have no idea what it is, but I'm going to add more photons. And as I do, you're going to see what it is. Okay, so that was a trick. It's not a galaxy. It is not an astronomical object. But if this image shows you how much light can be collected with a 6.5 meter telescope, this image shows you how much light can be collected with a 25 meter telescope. And that gain in collecting area is the difference between Magellan and GMT. Okay, let's do another example. We don't just need more photons, we need sharper images. So this is a bright image. I guarantee that no matter how many more photons I give you, you're not going to figure out what you're looking at unless I give you better resolution. So let me give you better resolution. And again, you will immediately understand that if you ever wanted to study any of these objects, penguins, you need to be able to separate them from the foreground and background of the image. You need sharp images. Okay, so now I will quit giving you trick images. I will give you an astronomical image. Okay, so illustrating these points together on the sky this time, here's a picture of the Whirlpool Galaxy, first taken with a photographic plate. And here is the same image, same object taken with HST. So what we want to do is make another major leap in what we can see in the sky. Sensitivity, more light, better resolution, better sensitivity. All right, so how much better can we do? Well, from the ground, image quality is limited by the turbulence in the atmosphere. So this image illustrates the limiting resolution you can get from the ground. This image illustrates what you can get from HST above the atmosphere. And in this case, the resolution is limited by the physics of light interacting with the aperture of the telescope. So this is called the diffraction limit of the telescope. And this limit gets better as the telescope gets bigger. So if we put a bigger telescope into space, like the next generation James Webb Space Telescope, we will be able to get better resolution. And in fact, JWST being a little more than twice as big, will have a little bit more than twice as sharp an image, twice as good a resolution. But JWST is about the biggest telescope we can imagine launching anytime soon. And so if we want to get sharper images, we'll need to build larger telescopes on the ground and correct the turbulence in the atmosphere. So that's what we're doing. And this image shows the resolution we expect to get with GMT using a technology called adaptive optics to get to the diffraction limit of the 25 meter telescope by correcting the atmosphere. Okay, so GMT will do this using adaptive secondary mirrors, and the design of the entire observatory is being developed from the start with this capability in mind. And this is a huge advance over the current generation of telescopes. Okay, so let's look at GMT. This view shows you the site, which is within, as Eric was saying, within Carnegie's Las Campanas Observatory in the Atacama Desert in Chile. And I'm going to start this. It's actually a movie. And as I do, you'll see the roads over this summit that lead to the rest of the observatory. And let's focus now on the enclosure. This is a 22-story building. It's a rotating building that is an engineering feat all on its own. And it has the crucial job of protecting the telescope and controlling the airflow around it. Now, as we were already hearing from Eric also, this is one of the best places in the world for ground-based astronomy. It's clear, it's got dry weather, very stable atmosphere, and dark skies away from cities. And now that we're zooming in here on the telescope itself, what you're seeing is the 7 mirror segments that make up the primary mirror of GMT. So these mirrors are shaped so that when they're held in place by the telescope structure, they form a single perfect surface to focus light, even though the mirrors don't touch. And you can also see the support structure, which is yellow at the top there, that supports the adaptive secondary mirrors that are the mirrors that actually do our atmospheric correction. Okay, so there are some pieces of information that are probably of interest to many of you over on the left. I'm just going to point out that in this drawing, you can see the telescope structure stands about 48 meters from the base of the pier foundation to the top of the secondary support system, and that the rotating mass is about 1,400 metric tons. Here are the mirrors themselves. These are technology at the heart of the telescope. Now, before I confuse you guys, these don't look like mirrors because they haven't been coated with aluminum yet. But remember, mirrors are just thin layers of aluminum on top of some hard surface, usually glass. And so what you're looking at here is the uncoated but perfectly formed polished glass that will be the mirrors once we've coated them with aluminum. So not only are these the largest mirrors ever made, but if you think about it, and you look at the picture, the little figure in the upper right, you'll realize that these mirrors on these 6 outer segments are not symmetric about their physical centers, meaning they're off-axis mirror shapes. And so this makes them extremely challenging to shape and polish to the nanometer accuracy that we need. But our partners at the Keras Mirror Lab in the University of Arizona have become world leaders in the technology of making and polishing and figuring these mirrors. And they've already completed 2 of these off-axis mirrors for GMT. So mirrors 1 and 2, segments 1 and 2 are already completed, and you can see one of those in the upper left. And 3 more of these mirrors are in various states of fabrication at the Mirror Lab. That's in the blue in the lower right. And the 2 mirrors, segments 6 and 7, we have the material ready to go for their fabrication. We've also already done all of the hard rock excavation needed for the foundation of the telescope itself and for the enclosure that protects the telescope. You can see the foundation of the enclosure illustrated there, pointed out there. And it's hard to get a sense of the scale from this picture, but let me just tell you that the enclosure foundation that's marked there is 60 meters across. So that's 2/3 of the length of a football field, roughly. So this leveled summit is enormous. Obviously, it takes an international collaboration to build something of this scale. And our partners are the universities and research institutions around the world that you see labeled here. So we've got partners in the United States, in Sao Paulo, Brazil, in Australia, and in South Korea. And then you can also see labeled in South America down there, the location of the observatory in Chile. And this is us. This is the GMT team in Pasadena. So we have a lot of people working with us who built the last generation of telescopes. And we have a lot of talented young engineers who are providing the psychic energy and the horsepower and the fresh thinking to get the telescope built. And you can see here also the names of some of the vendors around the world who are working with us. Okay, so I'm going to end there. And I hope I've given you a sense of why we're building GMT. And some of the first questions we'll use it to answer. But I want to emphasize we really have no idea what new questions it will raise, what new physics we'll learn, or how it will challenge our understanding of our place in the universe again. And I think that all that we will discover and all that we cannot guess we will learn is why it's important. And I hope you're as excited about this as we are. Obviously, I am. And I thank you very much for joining us today. So I'm going to stop sharing this. I can bring back up slides if it's useful to answer questions. But now I will hand it back over.
Thank you so much, Rebecca. That was an incredible talk with so many cool visuals. And I think if people weren't excited about GMT before you started, they certainly now.
That's the goal.
A lot of questions. So I'm going to try to get through as many as we possibly can and maybe to combine some of them so that we can try and get as many answers to folks as possible. So to start off with, Howard has, I think, a really great question to contextualize some things. He wants to know, what are the advantages and disadvantages of a land-based telescope like GMT versus a space telescope? And are both important for us to have as part of an astronomy strategy?
Yeah, I think both are important. So the fundamental limitations of being on the ground are the blurring from the atmosphere, which we, as I said, we can correct with adaptive optics. But the other effect of the atmosphere is also that it limits the wavelength range of light that can get all the way to us. So we can't see very far into the UV, and we can't really see very effectively into the far infrared, and the warmth of the planet itself brings up the relative background brightness of the sky. So I think that it's important to have both, and that they are very complementary.
And from that sort of big picture question, we have a number of really specific questions about the engineering of GMT. And here's one that I think pretty much everyone who hears about it asks is, Michael wants to know, how do the mirrors get from Arizona to Chile?
I don't know, but I'm not going to be there to watch. No, I can tell you they take a complicated trip. We put them on essentially a flatbed truck with a police escort, or at least I know exactly how the last set of mirrors went down to Las Campanas. And I suspect that we will end up doing it exactly the same way. I think this is the plan for how we will do it. So they get put on a flatbed truck and driven to the port of Los Angeles, I believe, where they get onto a ship, and they're tied down like cargo onto that ship, and they are taken by ship down to Chile and then carried again by truck up to the mountain, usually with police escorts at both ends on the ground. That's a good question. It's a terrifying journey. It's one of those things where you really do want to be sedated the whole time.
That's hilarious, but completely understandable. I feel anxious just hearing you talk about it.
Yeah.
We have a sort of similar question from Shane about, you showed how the building will rotate, and he wants to know what the engineering challenges of constructing a rotating building that will have this incredibly fragile and really irreplaceable equipment inside of it.
Whoa, I don't even know where to start. It is actually almost as challenging as the design of the structure of the telescope itself. So the foundation has to be able to support very smoothly the rotation of the upper structure. We need to control very accurately the flow of air and the temperature in the dome. So we pay a lot of attention to what we're doing with heat, where we're dumping the heat that various motors around the whole structure and the telescope itself produce. So yeah, there's too much there to unpack within a single 1 hour lecture, but it is absolutely a huge technical challenge, and there's much more information on our website about that.
You could come back and give a whole second talk just about the building.
That's right. I might be able to suggest somebody who could do that one better, but we could do another one.
So we have a couple of questions from folks, Simon and Jim, who are both asking about the issue of light pollution and whether that is a concern, both light pollution in Chile and then also things like the Starlink satellites, and what are the issues related to that?
Yeah, let me start with the Starlink satellites. So this is of a lot of concern to astronomers around the world. And we have already formed consortia to talk with these companies about the impact that satellites will have on observations of the night sky. And the response that we've gotten so far is that certainly for the first company that we're worried about, SpaceX, they're very concerned, and they're working with astronomers very diligently to try to reduce the reflectivity of the satellites and understand how we can minimize the impact. So I think the best we can do is keep talking with these companies. I think, and I certainly hope, that SpaceX will set a good precedent and really pave the way, helping us to influence the companies that come after. So we're definitely working on that. There is some city light that's now visible in Chile. When I first started going down to Las Campanas about 20 years ago, and certainly the people, my colleagues at Carnegie who've been going down there longer than I have, know that when 20 years ago, you basically couldn't see any city light. It was pitch black at night. It was really amazing. And now you see a little tiny bit of glow from a few communities down along the Pan American Highway, and you can occasionally see cars on the Pan American Highway. And we're working again within Chile. We have a large, there are a lot of astronomers in Chile, and we have our representation and our observers and people who run our observatory and other observatories in Chile, all working with the Chilean government and the local governments to limit this problem. So it's creeping in there, but it is nothing like you see in the United States, and I have confidence we'll be able to keep this minimized.
That's very good news. So we have a few questions about what the next generation after GMT's generation is, and Jackson wants to know, will we ever reach sort of a technological limit in which we can't improve telescopes anymore? And then Daniel wants to know, will there ever be a ground-based telescope on the moon?
Wow, those are great questions to which I wish I knew the answer. We're always, pushing up against the technological limits of the day. And one of the great things about ground-based telescopes is you don't launch them, which is really lowers the stress for those of us building the telescopes, to be honest. And it also means something very important, which is we can update the technology. So you don't think about this very often, but if you launch something, everything that you're launching has to be space rated, and that takes time. And so the technology that you can launch is actually old by the time you launch it. So the technology used on the ground in our ground-based telescopes is much more current, and we can update it constantly. We are constantly building new instruments for these telescopes. And that's really important because the telescopes collect the light and they make that sharp image, but then we put big cameras, the size essentially of VW buses, and big spectrographs on the back end. And those are what really allow us to analyze the light. And so by constantly upgrading those, we really make important advances throughout the lifetime of the telescope in the capabilities of the observatory. And about telescope on the moon, I have no idea. I am eager to find out if we're ever going to do that myself.
I can only imagine the challenges involved in constructing something like that. You think moving the mirrors to Chile are...
yeah, imagine getting the mirrors there. That's a harder trip.
Speaking of mirrors, we have a question from Joel who wants to know what's special about the glass from which the mirrors are constructed.
So one of the companies that I showed on my last slide is the company that provides us with the glass for those mirrors. It's the Ohara Corporation of Japan. And it's a borosilicate glass that can be melted. So the way we make these mirrors is very interesting. So you can imagine, if you just had a disc of glass, you can imagine how much material you would have to remove to figure it to the right shape. And it would take you, the rest of your lifetime to remove that much glass by polishing. So the University of Arizona has developed a very interesting technique of spinning the mirror to get it roughly to the right shape, just by the centrifugal force that pushes the glass up the edges of that structure as the mirror is spinning. So you spin cast these mirrors, and the glass that we use is a very special kind that's both very stiff and rigid and enables it to be melted in this way for spin casting. So I think I answered the question, but I have to admit I got so carried away there that you might have to repeat it for me if I didn't.
No, I think that was the perfect
answer,
and just fascinating to think about those mirrors and how they are made. So we have a question, moving back more into the technological realm. We have a question from Lida who wants to know about sensors used by the GMT and what advances in sensors it will incorporate or will be needed to be developed to take full advantage of it.
Okay, that is a great question. We use different kinds of sensor technology depending on the wavelength of light. So GMT will work in the optical to the infrared. And in the optical, we use essentially the same kind of detector called a charge coupled device, a CCD, that you have in your cell phone. Whoops, turned that on. In your cell phone and in your little handheld digital cameras now. And for the infrared, we use a variety of different detectors that actually, the technology is always developing in the infrared detectors very rapidly. And it's true that actually the performance of GMT will improve as the detection technology improves across the full spectrum of light, but particularly in the infrared.
And then we have a related question from Heather, who she refers to. We had a talk about a month ago, maybe 6 weeks ago, from some other Carnegie astronomers, Nick Hondaris and Gwen Rudy, and she refers to their talk and the instrument that they talked about building, and wonders from a size perspective, since the mirrors for GMT are so big, does that mean the instruments are also that much larger as well, or is that not a factor?
That is a fantastic question. So yes, it turns out that for at least two reasons, the size of the instruments has to scale linearly in one dimension with the size of the primary mirror. So the size of the primary mirror is directly proportional to the size of the image in the focal plane. So if in the focal plane you formed a picture of the moon that was this big with Magellan, the moon was literally this diameter in the image that was formed in the focal plane, that image would get 3 times bigger, or more than 3 times bigger, 4 times bigger, when in the focal plane of GMT. And what that means is that if you want to look at the same size field of view on the sky and you want to look at the same size object, you need the front end of those instruments needs to just scale up linearly with the size of the primary mirror. The other reason that instruments have to get bigger is because spectral resolution that you can get, it turns out, also scales linearly with the size of the primary mirror. It scales with a bunch of other things, but it also scales linearly with the size of the primary mirror. And so that means that the whole spectrograph behind that front end also scales up. So you end up scaling up in all dimensions, and the size of the optics also has to get bigger. So yes, the instruments scale proportionately with the telescope. And that is a big deal because it turns out that the instruments are almost as challenging as the telescope. They're not as large, but they have their own challenges. They're much more complex in and intricate in how they operate in many respects. And they have to move with amazing precision on their own. And so both the size and the technical difficulties become more and more of a challenge as the telescope gets bigger.
So we have another instrumentation question. This person asks, Eric referred to instruments you've built in the past for Carnegie's Magellan and at other places. How does someone like you approach building an instrument for an existing telescope versus a brand new telescope that's still under construction? Is that different? Is that a different approach, or does someone think about that in a different way?
Well, that's another really interesting question. So I think it's really important that the instruments be considered, when you're designing telescopes, that the instruments be considered along with the design of the telescope. And that is because fundamentally, there's sort of two jobs that the telescope has. It supports these amazing primary mirrors and focuses the light down to that focal plane and forms that sharp image. But the other thing it does is support these So you really need to think about how you're designing the telescope and the instruments together at the same time to make sure that they'll function together well and that you can actually build the instruments for the telescope. So for existing telescopes, you know, you sort of understand the performance and the capabilities and all the interfaces of the telescope already because it exists in their previous instruments. And when you're thinking about instruments for telescopes that aren't yet built, you have to be very, very careful that those concepts sort of come along together. And so we're in the process of doing that now.
We have so many questions that we are not going to get time to answer today. Unfortunately,
Those were all great.
To this
I
program.
thank everyone for those. Those are really good.
And we definitely want to invite folks who, we have time for one last question, but we want to invite anyone whose question was not answered to please send them to us via email to events@carnegiescience.edu. We'll make sure they're conveyed to Rebecca and that you'll get answers since we're running short on time. I want to ask a really fun question from Glenn to close out the program. He notes that today is the anniversary of the solar eclipse that many people, including Rebecca, were in Chile for last year, and he also was there. And he wants to know if you have any special recollections of that day.
Wow, that's an interesting question. You know, there was an eclipse in North America a year and a half, maybe earlier. I think that's right, in the summer. And I had a very profound reaction, actually, to the first eclipse that I saw, which was that one that previous summer in North America. And it made me, it did strike me as just an amazing sense of connection with the universe and also with humanity. You know, that this was an experience many people had. You know, all of mankind, essentially, who was lucky enough to live in the path of a total solar eclipse going back to the dawn of time, had been struck in the same way, even though we understand, you know, what's going on. And so it really gave me this very peculiar sense, not just of the universe, but of the continuity of mankind. And that I did not expect. That I really did not expect.
Well,
that's my primary memory of the day.
That's a lovely way to close the program. And now we would like to have GMTO President Robert Shelton give a few concluding remarks.
Well, thank you, Natasha. And Rebecca, thank you. I add my voice to the many to say it was outstanding, not only your inspirational talk, but the way in which you were able to respond to questions of great variety. It was a stimulating presentation. Thank you. I also want to add my appreciation for all of you who are participating in this event today. It's a pleasure to join you, and I want to thank you for your time. It's a very precious commodity, as we know. I have been part of a number of really exciting activities in my career, but I will say that the GMT is unique and special. As Rebecca demonstrated, we have many reasons why we're building this massive telescope, but they are primarily the science drivers that will take advantage of GMT's unprecedented capabilities. You heard a number of these possibilities, but I ask you to remember one in particular, one motivation for just this moment, and come back to it. In some ways, I think it's the most compelling mission of the GMT. It goes back to Rebecca's response to the last question, and that is the possibility that we will detect chemical signals of life outside the solar system. That really puts humanity in perspective. Now, to be sure, the GMT is an enormous undertaking. To build this, we require an international consortium. These are world-class universities and institutions. Rebecca showed you the map that lists the 12 founders. We call them founders of the GMT. And you can see that these founders reflect the broad partnership that brings together the scientific, the technical, and the organizational strengths. And we must have all of these strengths to ensure success. Our prestigious partner organizations join GMT because they share the passion that you've heard today in Rebecca's talk, and they want to ensure that their world-class astronomy departments remain at the forefront of the field for coming decades. If you want to be in the forefront of astronomy 10, 20, 30, 50 years from now, we feel this observatory has a lifetime of 50 years, then you need to be part of this. I use the word forefront, and of course, at the forefront of this effort is Carnegie Science. Carnegie Science's preeminent position in astronomy attracts the very best astronomers and scientists. Their talent helps guide us as we create the GMT, and we go after the most interesting scientific questions and future discoveries. As you've heard, the GMT is going to discover things we can't even imagine. Carnegie's membership in the GMT also guarantees them valuable observing time for their students and postdocs for generations to come. So before I close, Eric, I want to take this opportunity to thank you for your leadership and your partnership with the GMT. When this project is complete, I should say when we start observing, it'll never be complete because, as you've heard, we will continually be putting new instruments with better and better electronics and resolution power onto the telescope. But when it's complete, ready to operate, it will be the largest public-private funded science project ever. We are recruiting new university partners. We are partnering with philanthropists and foundations, and we're working with the US federal government to close the gap of funding during this and therefore realize the dream of the GMT. As you also heard, observations with the GMT will produce groundbreaking discoveries, fresh perspectives, and again, in Rebecca's talk, you've seen how astronomy over the millennia introduces entirely new fields of study. So I end the way I started by thanking all of you for your interest in this project. Your support will make us stronger. Joining us in this journey will hasten the success, enable discoveries we can't even imagine. So thank you all for being with us. And thank you, Eric, and your team for making this possible today.
So thank you, Robert. Thank you so much for your incredible leadership of this incredible project. And thank you, Rebecca, for a wonderful presentation. I hope everyone enjoyed it as much as I did. We are certainly at Carnegie very proud to be one of the founding members of this remarkable telescope, and we look forward to the years of discovery science with it. I also want to thank all of you in the audience today for joining us, for your interest in the Giant Magellan Telescope and in Carnegie Science, and hope you'll come back on July 23rd when Yishan Zhang, who is director of our embryology department, will be talking about some of her research, looking at symbiotic relationships between coral colonies and the algae that support their life. It's also what gives it color and hence bleaching when it gives up its life. She'll talk about the genetic underpinning of some of this interesting symbiotic relationship, but also how global warming is disrupting the relationship and threatening coral reefs across the globe. And I'm sure many of you know about that challenge. So please mark your calendars and join us on July 23rd. And as always, we appreciate your interest in us in Carnegie Science, and have a great holiday weekend. Thank you.